Hi, so this is the sixth class of the RA, sorry, TA, our practice class, and today we are going to deal with some our practice thing about the interval estimation. Actually, the estimation thing, but especially for the interval estimation, as there is nothing special thing about the point estimation. So we are going to skip for this our practice, and we'll start from the interval estimation thing. So as I already said in the last week, estimation is actually the most important thing, one of the most important thing in statistics, because we can estimate some parameters from our sample. So we can guess what population parameter is, and can get some information from the population, from the sample. So let's skip this one. And today we are going to deal with the interval estimation thing, because you already know how to construct the confidence interval, especially for the 95% confidence interval or any other confidence interval like 100 multiplied by 1 minus alpha percent confidence interval. So if we have our confidence interval thing, we can say that we are 100 multiplied by 1 minus alpha percent, sure that our parameter mu or any other parameter is included in the interval or not. So we can say like that with this confidence interval. This is what interval estimation says about, yeah, to me, to us. And the most important thing is that we have this formula. So it is actually the most important thing, so you should focus on this formula. So there are two situations, uh, depending on the knowledge about the sigma, which is a population standard deviation. So if you know that if we know the sigma information, we can use the formula from upper side. And if we don't know that our sigma, if we don't know the sigma information, we use the formula below. In this case, S is the standard deviation from the sample. So even though we don't know the sigma information, we are still able to use the standard deviation from the sample, so that we can construct the confidence interval thing still. So actually, you can see that this is the t distribution, not the normal distribution. So this is the first time to see the t distribution now. So it is important to use this distribution also from now on. So actually, as I already know, student t distribution is also very similar to the normal distribution, but it has a different shape slightly, and it takes just one parameter, which is the degree of freedom. So we usually call it df, which is the abbreviation of the degree of freedom. So it is n minus 1, and you can see that this is also pear shaped like normal distribution, but actually these two distributions are different from each other, because it depends on whether we know the sigma or not. We use different distribution from each other. So we are using the different distribution depending on different situations. So make sure that, please. So it means that we also have to know how to use the distribution in our programming. I mean, our studio. So as I already know, this is the contrary thing, maybe. Yep. So before that, as you already know, if we want to utilize some function dealing with the distribution in our programming, we always use D or Q or P or R, which means that if let's say that we are using a normal distribution in this time, when you want to get the density of the normal distribution, we use the normal denorm function with the three hyperparameter, like the x is equal to 0 and mean is equal to 0 or standard deviation is 2. And then we can get the density from the arguments. Or if we want to get the CDF value, we use the pnorm with the same hyperparameter. Or if we want to get the container value from the normal distribution, we use qnorm. Or rnorm for getting the random sample from the normal distribution. So it is actually same thing when regardless of our usage of the distribution. For example, if we are using the uniform distribution, we are using the same types of the function like d unip, r unip, p unip, q unip. So in the same sense, if we want to use the t distribution, we use dt, pt, qt, and even rt function. So actually, the usage is the same as the other function. So there will be no difficulty for you to use this kind of functions if you are already familiar with these kinds of function in our programming. So especially for the qt function, we can get the quantitative value from the t distribution with the hyperparameter as degree of freedom is equal to 5. And we can also set the lower tail option. And I think from now on, lower tail option is becoming important, I think, because we are using some quantile. So I think this is from now on, it is important for you to use the quantile function from now on. Because we always have to get the quantitative value when we have to construct the confidence interval from the distribution. So as far as I know, we usually have to get the right side of the quantitative value. I mean the right side of the probability of our own distribution. So I think which is same as this formula, and I think it is time to use the lower tail option as false. So let's see the example. So this is the problems which ask us to get the quantitative value with this percentile and this degree of freedom. So actually these 5 codes are the answer code for this solving this problem. So let's say that we want to get the first problem in this page, and if we want to get the quantitative value when our degree of freedom is 13, and our percentage value is 0.25. So which means that we want to get the 0.25 as a probability when our target when the probability is more than equal to our target value x. So we want to get this quantitative value from now on. And I think the code is somewhat incorrect because in this part, this is for getting the probability as, which is the alpha divided by 2. So because alpha divided by 2 is 0.25, then alpha has to be 0.5. So yeah, I think it is okay. So mm, yeah, I think it's okay. Yeah, never mind. Sorry. So if you want to get the quantitative value when the probability is more than equal to our quantitative value, our target value is 0.25 with a degree of freedom 13. To get the answer, we use this code. So our percentage value is 0.25 with the degree of freedom as 13. And because we are getting the right side probability, we have to use the lower tail option as first, not true, with the in the qt function. So you can see that the answer as 0.69. So this is 0.6938. You can check if it is correct. So this probability has to be 0.25. That's it. Okay, then so actually it is very simple algorithm. If we know that our sample comes from the normal distribution and it depends on different situation, so if we know the information about the sigma squared, which is the population variance, we use jet variable, which is related to the normal distribution. However, if we don't know the information of the sigma squared, we use t distribution and t variable. And on the other side, if we know that we are not sure that our sample comes from the normal distribution, we always rely on the sample size. So if our sample size is enough, big enough to get guarantee from the central limit theorem, we are still able to use the jet variable, which is from the normal distribution. However, if we are using the sample size as very small size, we cannot use any parametric statistics. So in this case, we are not able to use the estimation thing here. So actually, there will be only 3 cases because this class is just the basic class. I mean the introduction class of the statistics. There will be only 3 cases in our problem. So what you have to do is just classifying what situation is and do the same thing along with our algorithm, depending on whether you know that you're sure that our sample comes from the normal distribution or not, and also depending on the fact that we know our sigma squared information of the sigma squared or not. We use JIT or T distribution. So let's do that. So example number 1. Let's read this problem, and you can see that our population follows normal distribution. So in this case, we are in this. So we are here because we know that our sample comes from the normal distribution, and it also gives us some information about the average, which is mu. and even the sigma, which is 3. So this is time to construct the confidence interval for mu, which is the population mean. So because we know that in this case we can use this formula. So it already gives us the sample mean here, which is 4.5, and sigma is 3. So this is 4.5 now, and sigma is 3, and we also know the sample size here, which is 15. Then it means that we can now order value from the our programming, and we can also calculate this quantitative value from the qnorm function. So this is why I use the qnorm function for getting the quantitative value here. So because we want to get the 95% confidence interval, let's say that we want to get the 95% of confidence interval. It means that we have to get the qnorm quantitative value when our probability of our normal variable is greater than or equal to our quantitative value has to be 0.025, so that the summation of the both side probability results in 95%. I mean 5%, which is 0.05. This is why I used qnorm function with percentage value like this. And because we are using the standard normal distribution, we use mean 0 and standard deviation as 1. And make sure that we always use the lower tail option as false, because we always have to get the probability when our quantitative value is when our probability is greater than or equal to our target value. So because we have to get the probability when our quantitative value, normal value, is greater than or equal to. This is for this part, and this is why I use the lower tail option as false in this code. So please make sure that keep in your mind about this part, please, so that you can get lost. You cannot get lost whenever you solve any problem. And this is for sigma divided by square root of n, which is the same as this formula. Sigma divided by square root of n here, and this is per qnorm, and this is per x bar, which results in our lower bound of our confidence interval, because we deduct the result of the formula from our sample mean. And if we add two things, we can also get the upper bound of the confidence interval. So this is the how we got confidence interval from the normal distribution, when we know that our sample comes from the normal distribution, and we even know the sigma information, which is this part here. So this is the code or process for solving the example number 1. Actually, if you are already familiar with how to use the qnorm function or any probability thing, I think there will be no difficulty in using or solving this kind of problem. So that's it. And let me erase all the thing. And let's go to the second question. So it also says that the sample comes from the normal distribution. I mean, the population. It assumes that the population comes from the normal distribution. So we start with this part from now on when dealing with example number 2. And it even gives us the sample mean as 4.5, which is the same as previous problem. And there is also the information about the sample size, and which is the same as 15. And however, it says that the sigma is unknown, so we don't know what sigma is in this example. So, however, it gives us the information about the sample standard deviation, which is 3.5. So we know that S is 3.5 instead of sigma. So because we don't know the sigma, although we know that our sample comes from the normal distribution, we goes to this side because we don't know sigma squared. And which means that we also have to use the t distribution instead of normal distribution. So this is the time to use this formula here, because we know that x bar is 4.5 and n is equal to 15. And instead of sigma, we know s, which is what? Which is 3.5 in the problem. So it means that we can construct, for even now, the confidence interval of the population mean mu. And the most important thing is that we have to get the quantitative value from the t distribution with this information. And because we are getting the let's say that we want to get the 90% confidence interval for now, and I will leave the other thing, which is 95% confidence interval, as an exercise, but there will be no difficulty. So because we are going to get the quantitative value from the t distribution when our alpha is 0.05, because we have to get the 95% confidence interval, we have to get the probability when our probability, both of the probability has to be 0.05, which is 5% per each side, so that it can result in the 90% from the other area. So n minus 1 is 14 here. So from this information, we can get the quantitative value of the t distribution. So this is why I use this code for this answer. So the most important thing is to get the quantitative value of the t distribution. So this is why I used 0.05 as a percentage value as an argument of the quantitative function, and degree of freedom as 14, which is n minus 1, which is also 15 minus 1. And you have to also make sure that we are using the loyalty option as false, so that we can get the exact value of the quantitative value of our targeted t distribution. And then s divided by square root of n is same as this one. So after multiplying these two information, we deduct or add from the sample mean, which is 4.5, to get the 90% confidence interval for our population mean, which is mu, which is easy. So if you run this code, you can get the lower bound as a 2.9, about 2.9, and the upper bound is 6.09. So it means that our population mean, which is mu, is 9. We can be 90% sure that our population mean is included in this in this interval, yeah, with lower bound this one and upper bound this guy. This is what confidence interval says us to us. Sorry. And let's go to the third one. And so even though you read all the question, you cannot say that there's no information about the population distribution, so we cannot find any information about the population distribution in this question. So we are not sure that this sample comes from the normal distribution in this case. So we goes to this side because we are not sure that our sample comes from the normal distribution. However, if the sample size is big enough to get the CLT, central limit theorem, we can still use the normal distribution again. So because sample size is so big that we can use the central limit theorem, and it means that we can use the normal distribution again. So sample size is 100 and sample mean is 4.5, and it says the S is 3.5, and we want to get the 95% confidence interval now. So actually this is the same one, so we again have to use this formula. So 4.5 and root 10, and actually this is the important thing. Even though the only thing we know is standard deviation of the sample, we can use the information instead of sigma directly because central limit theorem guarantees that. So it is important that if we have large sample size, we can use standard deviation instead of sigma directly, even though we are not sure that our sample comes from the normal distribution. So this is why I use this code for getting the answer, and you can check the answer by running this code. And let's go to the last question from today's lecture. And until now, we have examined some formula about getting the confidence interval related to population mean, which is mu. However, from now on, we are going to get the confidence interval related to the population proportion. Which is the sample mean of proportion. So what I want to say is that we are dealing with different thing from previous one. So from now on we are dealing with the population proportion, not the population mean. So make sure that the situation is different from the previous one. And actually, we already know that if sample size is large enough, p bar, which is the sample proportion, has this normal distribution guaranteed by the central limit theorem, and this statistic follows the standard normal distribution, which means that we can also construct the confidence interval for our population proportion, which is p itself. So actually, we can also use this formula, and because we don't know what P is in this formula, we substitute the information with the P bar instead of P itself. So the most important thing, the most important formula is this one. So this is the last one. And so you can say that, you can check that sample size is so big, and so which means that we can use the central limit theorem and get the confidence interval without any hesitation. So sample size is 100, and we know that our p bar is 45 divided by 100, which is 0.45. So we can get the 95% confidence interval from now on. So what you have to do is just plugging in the information in this formula. So it says that if we know the quantity value and p bar, we can always construct the confidence interval. So this is why I used this code here. So this is the part for the getting quantity value from the normal distribution, and this is the part for getting the this part, square root of the p bar multiplied by 1 minus p bar divided by n, which is the same as this formula here code. So if you run this code, you can get the confidence interval for getting the population proportion, or even the upper bound. That's it. So actually I just repeated, I think I repeated the same procedure when constructing the confidence interval, but it is important that we follow each algorithm when we solve the question. So it depends on whether we know that our sample comes from the normal distribution or not, or whether we know the information, the value of the sigma squared, which is the population standard deviation, population variance. So, and you also have to be sure that there is also the formula for getting the population proportion confidence interval with the designated confidence interval, percent of confidence interval. That's it. So so you can feel that, I think you can feel that the importance of understanding the usage of the function of qnorm or qt function from now on. So it is the reason why we have dealt with the for the functions in our programming before the midterm examination. So because we are repeating actually the same thing until the final examination, and there will be also some or many problems will deal with this kind of code or this kind of formula. I think you have to understand if you are not familiar with this kind of concept. So after I summarize this lecture in Korean, I will end this class, and thank you. 안녕하세요. 그래서 오늘 실내 구간에 대해서 했는데, 결국 솔직히 제가 생각해도 좀 복잡하긴 한데 결론은 되게 간단하거든요. 그래서 좀 더럽긴 하네요. 어쨌든 저희가 샘플을 가지고 있는데 파퓰레이션 샘플 민이 있어요. 그러면 population mean은 어떻게 될까를 궁금할 수 있잖아요. 그때 사용하는 게 신뢰 구간인 거죠. 그래서 95% 신뢰 구간을 만약에 구해요. 그러면 저희는 이제 이게 3이고 이게 7이에요 만약에. 샘플 미는 대충 5인데 그러면 저희는 이제 95% 확신할 수 있어요. 어떻게? 저희의 아직 모르지만 population minim한 건 사실 절대 모르는 거지만 95%는 확실하게 3이랑 7 사이에 있을 거다. 뭐만 가지고 저희의 샘플 민만 가지고 그거 알 수 있다는 게 바로 신뢰 구간입니다. 그렇기에 그거에 필요한 정보들을 안에 넣어주기만 하면 신뢰 구간에 있는 값들이 나오게 되는 거겠죠. 그래서 저희 샘플 민에서 퀀틸 밸류랑 이걸 곱한 것을 빼거나 더하면 로얼 바운드, 어퍼 바운드가 생기는 건데 그게 시기, 상황에 따라 달라진다는 거죠. 언제? 우리 샘플이 정규 분포에서 왔는지 안 왔는지 왔으면 심지어 우리가 시그마 스퀘어를 아는지 모르는지 심지어 정규 분포에서 안 왔다고 해도 샘플이 크기만 하면 다시 노멀을 쓸 수 있다는 거죠. 그래서 상황에 따라서 이 밑에 식을 이용하거나 t 디스트리뷰션이면 아니면 노멀 디스트리뷰션이면 위에 걸 이용하시면 됩니다. 그리고 코드는 단순히 밑에 걸 이용하냐 위에 걸 이용하냐 아니면 알파가 뭔지 아니면 디글 프리덤이 뭔지 아니면 시그마나 S가 뭔지 N이 뭔지에 따라서 샘플 민이 뭔지에 따라서 그냥 똑같이 넣어주기만 하면 돼요. 그리고 저희가 컨테일 밸류를 구하는 게 qnom 아니면 qt 펑션이잖아요. 거기서 로열티 옵션을 폴스를 쓰는 게 중요한데 그게 왜냐하면 저희는 신뢰 구간을 구할 건데 이 양쪽 사이드에 있는 probability를 알아야 되거든요. 그래서 만약에 95%면 이쪽 각각이 2.5%가 돼야 되는 거죠. 그러니까 0.025여야 돼요. 만약에 한쪽이. 그러면 예를 들어 95%면 0.025만큼의 퀀티 밸류가 뭐냐 이걸 딱 가르는 x값이 뭐냐를 알려주는 게 퀀틸 펑션이잖아요. 그래서 디그리 프리덤이랑 퍼센테이지 밸류를 넣으면 그걸 맞는 값이 딱 나와서 이 x를 알게 되는 거죠. 대신 이 값보다 오른쪽에 있는 확률을 알고 싶으니까 로열티 옵션을 폴스를 쓰는 겁니다. 그리고 시그마에다가 스퀘어 루트 오브 n을 나눈 값을 곱해주면 여기 컴피턴스 인터벌에 있는 포뮬라를 그대로 쓸 수 있게 되는 거죠. 하여간 비슷한 걸 계속 똑같이 하는데 한 번 이해하면 정말 쉬울 거라고 생각을 하고요. 제일 중요한 거는 문제에서 사실 어떤 상황인지 알려주지 않잖아요. 이 하나, 둘, 세 가지 상황 중에 어쨌든 한 가지 상황으로 나올 텐데 문제를 통해서 알아서 유추를 해야 된다는 거죠. 뭔가 예를 들어 수능 같이요. 수능 문제처럼 알아서 이제 어떤 상황인지 알고 그거에 해당하는 공식에다 그냥 넣어서 컴퓨터스 인터벌을 구하고 결론을 내면 됩니다. 근데 이게 진짜 중요한 게 지금은 포인트 에스티메이션, 컴피던스 인터벌레이션 하지만 컴피던스 에스티메이션 이제 앞으로 기말까지 저희가 계속 할 게 가설 검정이거든요. 하이퍼서시스 테스팅. 근데 거기서 계속 반복하는 게 지금 이 공식과 비슷한 결을 계속 반복할 거예요. 그러니까 저희는 앞으로 계속 퀀틸 펑션을 쓸 거고 앞으로 계속 이런 시그마, 엑스바를 문제를 통해서 알아서 구해야 되고 앞으로 저희는 항상 이런 상황이 우리가 이 문제가 이 상황 중에 어디 있는지를 파악해야 된다는 거죠. 그러니까 지금 만약에 이 내용이 너무 어렵다. 그러면 어떻게든 이해를 하는 게 정신건강에 좋습니다. 왜냐하면 앞으로 계속 반복할 거니까. 대신 이 뜻은 한 번만 이해하고 한 번만 대충 알코드 다 비슷비슷하잖아요. 그거 그냥 어떻게 넣는지만 좀 따라해보고 숙지하면 앞으로는 어려울 게 없다는 뜻입니다. 그리고 뭐 population mean을 했다면 마지막은 population proportion을 다루는데 저희가 이미 앞서 다뤘듯이 population proportion은 이렇게 하면 스탠다드 노멀 디스트리뷰션에 따르는 걸 알죠. 그 뜻은 confidence interval을 구할 수 있다는 뜻이고요. 여기서는 특히 p 발값만 알면 여기 보면 p 발밖에 없어요. 사실 우리가 넣어야 되는 게 그래서 이거 하나만 알면 한 번에 구할 수 있다는 겁니다. 조금 특이하게. 그렇다는 것이고, 아무튼 이 정도면 될 것 같습니다. 네, 감사합니다. Hi, I edit this video for because I just forgot some part of chapter 6, so I'm just acting supplementary video from now on. And in this part, we are going to make a simple experiment in which we repeat the simulation for constructing the confidence interval many times and see if we can be 100 multiplied by 1 minus alpha percent sure that our confidence interval have our population mean mu like that, because let's say that we have when we construct the 100 multiplied by 1 minus alpha percent confidence interval, let's say that our alpha value is 0.05, then we have a 95% confidence interval for now, which means that briefly we are 95% sure that our confidence interval with these two upper and lower bound have our population mu like that. However, this is not the exact expression because actually population mu is a constant value, so that we cannot say that our population mu, which is constant, is included in our certain interval with percentage. I mean, it cannot be located between in this confidence interval randomly because it is just a constant. So we have to say that our population mean mu is included in this interval or not, because this is just a constant, but we cannot say that this is 95% surely included in this competence interval. So what we have to say is that when we check that our population mu is if our population mean mu is included in this confidence interval, for example 100 times, 95 times, I mean in out of 100 times of experiment, 95 percentage of those experiment will be successful. I mean, if we have 100 times of experiment, then 95 percentage of the out of 100 experiment will be successful, which means that our population mean mu is included in this confidence interval out of 100 experiment. So what we are going to do this time is just repeating the same experiment about constructing the confidence interval many times and see if we are really 100 multiplied by 1 minus alpha percent sure about the existence of the population mean mu between the upper and lower bound. So actually we already know this formula, so constructing confidence interval is very easy from now on because we have solved some problems using this formula, and we have checked the answer before the previous time. So from now on, let's make some simulation thing and repeat the same simulation and see the result. Let's do it. So this, as you already know, our known function gives us the samples from the normal distribution with mean this value and standard deviation with this value. So in this time, we are going to make a 50 random sample from the normal distribution with mean value as 5 and standard deviation as 3. And we are going to store the result from the Arnon function into the sample one variable that we made for our own. So you can see that sample one variable has 50 sample from the normal distribution. And if we check the mean and standard deviation with the mean and standard deviation function, you can also see the standard deviation and mean of the 50 random sample from the normal distribution. So we can check the mean and standard deviation is similar to the hyperparameter of the Arnold function. Very similar to. And then because we have this formula, let's say that we are not sure that so let's say that we know that our sample comes from the normal distribution because we use the Arnold function, but we don't know the population standard deviation. In that case, we use the sample standard deviation instead of sigma. So I mean this case. So which means that we have to use the t distribution variable, random variable, which also means that we have to use qt function here. So because we are going to make a 95% confidence interval, our percentage value in the qt function has to be 0.025, and degree of freedom has to be sample size minus 1, which is 95, because our sample size was and is 50. And because we are doing the right side thing, you have to set the royalty option as false, which gives us the quantity value from the t distribution. And then after we multiply the value with the standard deviation of the sample divided by square root of sample size, we can get the confidence interval of the lower bound and the upper bound by deducting or adding from the sample mean. So this is just nothing but just getting the confidence interval, lower and upper bound for the 95% confidence interval. So after storing each value, we can check that our lower bound is about 4.31 and upper bound is 5.89. And then we can check that our population mean, which is 5, is located between the upper and lower bound. I mean, it is located in the bound of the confidence interval. So if S function gives us the second argument when the first condition is satisfied, in other words, if the first argument's condition is not satisfied, it gives us the third argument. So which means that if our population mean, which is 5, is between the lower and upper bound, it gives us the value 1. Otherwise, it gives us a value of 0. So we can easily check that because lower and upper bound has the value 5 within 2 bound, we can get the value 1 as the result of the if-else function. So we can check that it is a kind of true and false function. So if our population mean mu is between the bounds, we can get true value, which also means the 1. Or we get 0 value 0, which means the false value. And then because we are going to check and repeat the same experiment many times, we can use the for loop here. So this is the function. So this is the repetition function for giving us a empty vector. So full of NA value with 100 times. So if we check the true and false variable, you can see that it has the 100 NA value within the empty vector. So let's say that our index for now I is 1, and if you repeat the same experiment from the previous one, the same as the previous one, making the bound, after making the sample and getting the upper and lower bound, and after checking if our population mean mu is between the two bounds, we can also store the result of the effect function into the i's index of the true first variable. So after running this code, you can see that our true first variable has the value 1, in the first location out of the 100 NA value. Because we store the result of the effect function into the first location of the true false vector, because I value was 1 as we stored previously. So in this time, you have to know how it works, this index or effect function, or making the confidence interval. And from now on, we can really make the repetition of the same experiment many times. So let's say that we also have the same empty vector with a NA value. And as you already know, with for loop, uh, in this for loop, the I index goes from 1 to 100. So we can repeat we can repeat the same experiment with 100 times from I through 1 through 100. So in every experiment, if we get each result of the effect function, we can locate the result of the effect function into the ith index of the true false variable. And because true false variable has 100 NA value, we can, after this for loop, we can get all of the 0 or 1 value in the true false vector. It is somewhat difficult, but yeah, I will explain in Korean soon. Okay, and let's run this code now, and you can see that true false vector has this kind of 0 or 1 value here, and because this is composed of 0 or 1 value, I mean value with 0 or 1, if we check the mean of the true false vector, true underbar false vector, we can see the percentage of 1. The frequency of the 1 appeared in this true false vector. So if you check the mean of the true false vector, you can see that this is the 0.98. But it is somewhat different from the 95% because sample size is not that big. So if you want to get more accurate information, you can increase the sample size to 1,000 or 10,000. So after do it with sample size as the 10,000. So I mean not sample size but the iteration of the experiment. So after in this part, I will increase this iteration to 10,000, and in the for loop we also have to increase the I value through 1 to 10,000, and then you can see that true false value has the 10,000 vector. I mean true false vector has 10,000 value in this vector. So after you check the mean of the true false vector, you can see that it is about 0.954, which is very similar to the 95% confidence interval, which means that we can get what we constructed is the 95% confidence interval exactly. And if you increase more and more the number of iteration, you can also get the more accurate percentage of frequency of 1 in the super spectre, like that. Actually, the second thing is about nothing but just doing the same thing with the different percentage confidence interval. So you can see that because we are dealing in the 95% confidence interval, we have to use the percentile value, which is p argument in this Qt function, as 0.05. Previously, it was 0.025 because the percentage is different, 95% or 90%. So make sure that based on the percentage value, we have to modify the percentage value in the Qt function. And the other thing is the same. And let's increase the iteration to 10,000. And if you see the result, you can see that the mean value is the 0.8948, which is very close to the 95%. So which means that we managed to construct the 95 confidence interval, because if we repeat the same experiment in which we check if our population mean mu is between the lower and upper bound of the confidence interval that we made about 10,000 times, we can see that 9,000 experiment was successful, was good at including the so in yeah, okay, let's say again, out of the 10,000 experiment, the 9,000 experiment were successful to include the population mean mu between the lower and upper bound, which means that which means that we got the 95% confidence interval this time. So this is how we got the simulation of confidence interval and check if we really made a 95% confidence interval or not, or a 90% confidence interval. So it is just based on the percentage value of each simulation. And I will end up this our practice after explaining Korean also. Thank you. 안녕하세요. 그래서 제가 빼먹고 놓친 부분이 있는데 바로 컨피던스 인터벌을 시뮬레이션 하는 부분이거든요. 근데 이게 좀 헷갈릴 수도 있지만 어쨌든 중요하니까 한번 다뤄보려고 영상을 추가적으로 찍었습니다. 그래서 결국 저희는 95% 컨피던스 인터벌도 만들어봤고 90% 컨피던스 인터벌 만들었잖아요. 근데 이게 도대체 뭘 의미하는지를 따져보는 게 사실 이 시뮬레이션이거든요. 왜냐하면 95% 컨피던스 인터벌이 한마디로 직역하면 우리는 이 인터벌이 95%의 확률로 우리의 파퓰레이션 민 뮤를 포함하고 있을 것이다 라고 예측할 수 있는 게 바로 신뢰 구간이잖아요. 컨피던스 인터벌이라고. 근데 사실은 저희 모수인 파퓰레이션 민 뮤는 상수이기 때문에 95%의 확률로 존재한다고 말할 수가 없어요. 왜냐하면 예를 들어 뭐 상자 안에 어떤 물건을 넣는데 그럼 너는 저희가 예를 들어 95%의 확률로 뭔가 존재하는 구간을 만들었어요. 근데 그게 정확하게 이 상자 안에 내가 넣은 물건이 95%의 확률로 존재할 것이다라는 것을 나타내기가 애매하잖아요. 왜냐하면 있으면 있는 거고 아니면 아닌 거지. 95%의 확률로 있을 거다라는 건 말하는 건 애매하기 때문에 좀 더 정확히 말할 수 있는 것은 사실 예를 들어 저희가 100번의 실험을 하면 저희가 샘플을 추출해서 저희 파퓰레이션 민 뮤가 샘플 민으로부터 발생된 이런 컨피던스 인터벌 안에 포함이 되는지 안 되는지를 따져봤을 때 100번 중에 95번은 들어올 것이다. population mean 뮤가. 그러니까 이 confidence interval이 population mean 뮤를 95개만큼은 잘 추정할 것이다. 100개 중에 라고 하는 거죠. 예를 들어 10,000개였으면 9,500개고 그렇게 말하는 게 사실 좀 더 정확한 표현입니다. 그렇게 말하는 것을 잘 표현하기 위한 시뮬레이션이 바로 오늘의 코드인데요. 한마디로 사실 이거 로얼 바운드 세우고 어펄 바운드 세우는 거는 이미 저번에 했었고 여기서는 그 어펄 바운드, 로얼 바운드가 population mean 뮤인 5보다 그 5를 포함하고 있냐 맞으면 1을 주고 아니면 0을 준다는 게 if else 펑션이거든요. 이걸 한 번 할 수 있으니까 이거를 for 루프를 이용해서 10,000번을 해보자는 거죠. 저희가 일일이 10,000번을 해서 셀 수는 없으니까. 그러니까 R 프로그래밍의 힘을 볼 수 있는 거죠. 한마디로. 귀찮은 거를 10,000번을 1초 0. 몇 초 안에 해버리게 하는. 그래서 10,000번이 trueFalse라는 베리어블은 벡터는 NA 밸류 즉 empty한 밸류를 10,000개나 일단 주는 건데 그 안에 첫 번째 로케이션부터 10,000번째 로케이션까지 ifelse에서 나온 결과 1 또는 0이 결과값을 계속 채워주는 거죠. 첫 번째 위치부터 10,000번째 위치까지. 그러니까 0 또는 1이 10,000개가 다 채워지는 거예요. 한 번에. 이 for 루프로. 어떻게? 일일이 50개씩 노멀에서 샘플을 해서 컴피던스 인터벌을 세우고 저희의 population mean 뮤가 그 컴피던스 인터벌에 들어오는지 안 들어오는지를 나타내는 지표인 거죠. 들어오면 1 아니면 0. 그거를 10,000번 반복한 겁니다. 그런 후에 true and false 벡터를 보면 1 또는 0이 10,000개가 있을 거잖아요. 이렇게 지금 9,000개가 빠져있다는 뜻이고 첫 번째 밸류부터 1,000번째 밸류까지 1 또는 0이 있고 총 10,000개가 있겠죠. 근데 저희가 그러면 1이 들어와 있다는 거고 0이 안 들어와 있다는 거잖아요. 그러면 그 1이 몇 개가 있냐를 세는 게 사실은 min 펑션을 이용해서 이 벡터의 min을 그냥 구하는 거랑 똑같아요. 왜냐하면 사실은 min이 정의 자체가 sum 나누기 개수잖아요. 10,000개. 근데 어차피 각각 값이 1이기 때문에 1을 싹 다 더해서 만으로 나누는 거나 min을 구하는 거나 값이 똑같다는 겁니다. 그러니까 어쨌든 1이 여기 몇 퍼센트만큼 있냐를 알려준다는 점에선 똑같다는 거죠. 좀 더 유식하게 표현한 거죠. 한마디로. 그래서 뭐 어떤 걸 구하시든 0.9527이 나오게 됩니다. 즉 저희는 10,000개를 돌렸더니 실험을 9,527개는 컴필레이션 뮤를 포함했다. 저희가 만든 컴피던스 인터벌이. 그러니까 저희는 95% 컴피던스 인터벌을 만든 게 맞다 라고 볼 수가 있는 거죠. 그러니까 이렇게 말하는 게 사실 몇 퍼센트 컴피던스 인터벌이라는 의미에 좀 더 근접하게 잘 말한 것이라는 뜻입니다. 실험 자체가. 그래서 90%의 컴피던스 인터벌은 똑같죠. 하면서 의미는 똑같은데 90% 컴피던스 인터벌은 어떻게 만드냐. 여기 큐티 펑션에 있는 퍼센트의 밸류를 조정하면 됩니다. 원래는 95%였으니까 양쪽에 2.5%씩 빼야 되기에 0.025씩 한 거죠. 여기서는 90% 컴피던스 인터벌이니까 양쪽에 5%씩 빼야 돼서 0.05를 퍼센트 밸류로 넣은 것입니다. 그런 차이만 있을 뿐 전체적인 실험의 과정이나 결과는 똑같고요. 충분히 어려울 수 있지만 앞으로 중요해질 내용이기 때문에 한번 다뤄봤습니다. 그럼 감사하고 다음에 뵙겠습니다.